Okay, so the majority of the test is on solutions. And remember, a solution has two components to it that are homogeneous. It could be two solids, two liquids, two gases, a liquid and a solid, but they have to be homogeneous. Think of vodka. You can't tell the difference between ethanol and water in vodka. So that's a solution. Think of a gold ring. It's got copper and gold in it. Can't tell the difference between the copper and the gold. The air we're breathing is a solution. Can't tell the oxygen from the nitrogen, from the carbon dioxide, etc. Now, as far as your test tomorrow, you're going to be doing two main things, a quantitative part and a qualitative part. The qualitative part is this here. Describe in detail how a cube of sodium chloride dissolved in a water solvent, including both verbal description plus a diagram. I want you to show the hydration sphere. I want you to describe how the crystal dissolves and the two forces involved. Okay, so it's going to be something like this. Okay, so that's the crystal of sodium chloride. And remember, water is not a symmetrical molecule. It's got negative parts and positive parts. So the oxygen part is partially negative. That's what that little squiggly line means. And the hydrogens are partially positive. Now, the little squiggly line is actually a Greek letter delta, lowercase delta. And when you get into calculus and differential equations, you're going to have a partial differential equation, and the D's are those. And that's where the partial comes from. Okay, so basically we've got a polar crystal in there, and the water molecule is going to pull out the sodium and pull out the chlorides. So that negative oxygen is going to pull out this positive sodium ion. And those positive hydrogens are going to pull out the negative chlorides. Excuse me. So everything is moving unless we're at Kelvin 0. And because everything is moving, these water molecules are bouncing up against that salt crystal. The higher the temperature, the more they bounce against the crystal, hence it dissolves faster. So the water is surrounding the sodium now as it pulls that sodium ion out. That's called a hydration sphere. And there's one for the chlorine as well. So both these are hydration spheres. So the sodium and the chloride no longer are together once the water pulls them out of that crystal. So these are the two forces acting on that crystal in the solution. Solvating force, which is pulling it out, and the crystal lattice force is keeping it together. Whichever is bigger wins. If the solvating force is larger, then it dissolves. If the crystal lattice force is larger, it doesn't dissolve. And then there's some gray areas where they're sort of even and it partially dissolves, but basically whatever one's stronger wins, whatever one's stronger either dissolves or stays together. And think about sand and salt. Sand's got a very high crystal lattice force because it doesn't dissolve in water, where salt dissolves very readily. So it has a very strong solvating force. Solvating force is a function of temperature. Higher the temperature, the stronger the force. So if the salt doesn't dissolve, you heat the water up and guess what? It dissolves because the solvating force increases with heat. So it dissolves it. So that's basically what I wanted for this answer. Yeah. That can affect the solvating force. Are heat, physical agitation, and surface area. Yeah. Yeah, to either dissolve or not. Huh? Yeah. So I need forces on there. I need a diagram. I need a little paragraph of you explaining how this thing works. Okay. Now I'm recording this so you can go back over this at home tonight. Okay. All right. And that's what that problem was getting at in that problem. Okay. What did it sound like? Yeah. Just kind of describe everything. That's all. How is it being pulled apart? You know, because water is got this polar molecule, it's got positive and negative parts. The negative is attracted to the positive parts, the positive is attracted to the negative parts. So it's attracted to it. And because it's moving, it pulls it out. All right, I've already talked about what a solution is. All right, so this is the quantitative part. How would you make 10 liters of a 0.200 molar solution of glucose, C6H12O6, from dry ingredients? Now remember, molarity is moles per liter. So we need to know how many moles of glucose are in that solution. So to do that, we're going to multiply volume times concentration volume is in liters, concentration is moles per liter. We have 10. And 0.2 moles per liter. This will give us right? No, it's 5. It's 2 on there. Okay. Now you can't go to the store and buy 2 moles of sugar, but you can buy grams of sugar. So we need to convert the moles to grams. Okay, and so that's the molar mass for glucose. Now it says, how would you make? I'm asking for directions. You have to do the calculation first. So to make this, we would dissolve Now, it doesn't matter on the volume you initially, as long as it's less than 10 liters. So let's say 8 liters. And it's 3 sig figs, so we need to do that. So that's the answer. Don't just give me numbers. I wanted a discussion or a description of how it's to be made. Yeah. Yeah, for sure. It's easier for me to type glucose than to put the subscripts and all that junk. But yes, and it won't be that giant of them. But yes, either way is fine. And you probably wouldn't know that C6H 1206 is glucose. All right, so does that make sense? This is the answer I want. I want a description of how to make it. Just as if you worked in the stockroom and you had to make this solution for a lab. This is the way you would do it. And the 9 or the 8 liters, it doesn't matter if it's 9, 8, 6, or 5, as long as it's less than 10. And the purpose of less than 10 is you need to get it completely dissolved, then bring it up to 10.0 liters. Because if you don't do that, you're going to end up with more than 10.0 liters in your final solution. Okay, so any questions about that? The answer has to be in a paragraph, just like that. That's how you'd make it. Doesn't say that, so it says, how would you make? Yeah, and you can't go to the store and buy 2 moles. All right. Okay. We're going to make the same solution now with a concentrated sugar solution. Yeah.
Solution?
That'll work. All right. Okay, so the previous problem, we looked at creating it from dry ingredients. Now we're going to make it from concentrated solution. We're going to dilute it. So this would be a dilution problem. So the first thing is to figure out how much of the concentrated solution we need. And so the moles are going to be the same for both the concentrated one and the dilute one when we add them in together. So we're looking at okay, it's the same formula. Okay, so we're going okay, that's where we want to end up. And again, that's the moles in the diluted one. And that's the same as the moles in the concentrated one. But we don't know the volume of the concentrated one. So it's a simple algebraic equation. We need to solve for liters. So we want 0.163 liters of the concentrated stuff. So the directions. Basically, we're going to take and start adding water to make sure that's totally homogeneous with the concentrated, and bring your volume up to 10 liters. So that's two approaches on making solutions. One starts dry, one starts concentrated. All right, what's the final sodium chloride concentration when 1.23 liters of 2.31 molar sodium chloride is dumped into another one? It's 2.12 at a different concentration. So basically, we have two solutions, not at the same concentration. We're dumping them together. What's the final concentration? So there's two steps to this. First step is to find out what the total moles are between each one of them, and then we dump them together, and that'll be the moles. And then we look at the volume each one contributes, add those together. So then we end up with moles per liter. So that's for solution A, that's what the moles are. On B, we're going to do the same thing. Okay, so we're looking at 14.84 moles total between the two of them. The total volume is going to be 335 liters. So we have 1484 moles and 335 liters. So that's 4.43 molar. That's how concentrated the resultant mixing is. So you find the total moles first from each beaker. What are they contributing? Then you look at the total volume. No, because the question is how concentrated is it? I didn't say how to make it. Okay, what's the difference between an acid and a base? Right, so with an acid, the H ion dissociates. With a base, it's the hydroxide ion, the OH. minus that disassociates. Strong acids, 100% disassociation. Weak acids, less than 100%. There are significantly more weaks than strongs. There are only 7 strong acids in our world that we know about. All the rest are weak acids.
Is that the word you use? Disassociates?
Disassociate.
Okay.
In other words, comes off.
Yeah, I know.
Okay, so we have one of the strong acids is hydrochloric acid. And so we have so that's our first acid. And it's balanced as written. Always make sure it's balanced. So it wants to know the hydrogen ion concentration. Well, because we have a balanced equation, we know the moles of HCl equals the moles of H. Moles of HCl equals moles of chloride, Cl, because it's a balanced equation. So we can do everything using HCl. And then we know that's the same as the H plus concentration. So we need to know the moles of HCl. We're not given moles, we're given grams. So we got to convert the grams. And chloride is what? Okay, so it'll give us moles of HCl. And all this is over 8.94 liters. So now we have moles per liter, which is concentration. So we're going to go so once we find the concentration of HCl, that's the same as concentration of H plus, because it's a 1-to-1 relationship from the balanced equation. Okay, so your practice test should look very similar to this. Okay, all right, a couple gas problems. We have the equations PV is equal to nRT, and then PV over T is equal to PV over T, initial final conditions. Those are the two equations, and I'll be giving you those. I'll be giving you R constant. We're working with atmospheres. Okay, so first problem, we want to know what the volume is. Now for the using the PV over T is equal to PV over T, those are changing conditions. Now this problem is not changing. I'll just say these are the conditions, what's the volume? So then we use the PV is equal to nRT. So solving for P, that's the same as nRT over P. All right, number of moles is 345. Bless you. R is T is 45.3, 273. So we're looking at what, 0.38 all over 124 atmospheres. Just a straight substitution into that. PV is equal to nRT. Now, the second problem is a changing condition. That means this is the one we're going to use, the PV over T is equal to PV over T, because the conditions are changing. We're looking at initial conditions, final conditions. So we're heating from 12 to 34 degrees. Okay, that's our initial and final temperature. And we don't know what the final volume is. We know the final pressure. Now, notice I didn't give you the final pressure. If the final pressure is not given, we assume the pressures doesn't change. Okay, let me just solve for the final volume, V. Now, how can we simplify this problem? Yeah, if we divide both sides by 234, the 234s go away. So they basically cancel out. So we don't have to worry about the atmosphere. We just have to worry about these two and this guy. So if we cross multiply the 307 over to here, that'll isolate the V. So if we multiply both sides by 307.5, 307's cancel, 307 on the top over here. Or if we cross multiply a 307, that just brings it to the other side. And the sign of the fraction's inverted. So the final volume is gonna be 25.3 liters. Now, had I given you a final pressure, we'd have to calculate in the pressure. And I think, yeah. So you got a couple gas problems. Tomorrow you will have a couple, excuse me, a couple gas problems. You're gonna have an acid problem. And then the remainder is gonna be some solution problems, and then the qualitative description of a crystal dissolvent. Which one? This one here? Okay, so we're done with the semester. Sad face. Summer's coming. Okay, so that's it for today. Let's see. We'll be finishing up our labs Friday, Saturday labs. And that's about it. For tomorrow. Will be after the test. Finals online, but test 5 is here. Which is similar to what I went over today. Are you gonna get extra credit? Is
Yeah.
that what you're asking?
Yeah.
Yes,
Where you're gonna put it in.
after you finish test 5.
Okay.
Because I don't know which one's the lowest.
Oh,
It applies to the lowest one. Unless you don't want me to apply to the lowest one, you can apply to anyone you want, but I would recommend applying it to the lowest one. That'll give you the most benefit.
You said, so this is like what you want us to draw for the answer.
Yeah, with a little paragraph explaining it, what's going on.
Okay. All right.
So basically in this, you need to include all this stuff. Sure. Do you know where Maida Toyota is? Maida Toyota. It's off of Madison, isn't it? There's a bunch of car dealerships there.